we did, how like the theory behind all of it, and how we implemented it, and the first results we got. To start with, I don't know, this is not really necessary. That was in case somebody would show up that is not really into Formula Student until now, so I think I can almost skip that. Like it's just the points that we have, like the track layout design and the cones that we will try to detect with our system. And here we have made a small overview about our system, like from input to output, what we actually wanted to achieve. Like what we have as our input are the cones, that typical Formula Student cones, like that you saw on the slide before, in colors orange, blue, and yellow. And then our input sensor is a camera. We will come to for two design choices later here, but was the original plan. Taking this data, going into a neural network, and afterwards post-processing the data and printing out 2D coordinates for the next module. First thing in our system is the camera. We, in the beginning, like you all know, we already had this camera from last year's team because they made the design choice to take this camera. We compared it to some other cameras in the beginning and came to the conclusion that we go best with this camera to just take this again. Just because like its resolution and the frequency it's running at and actually the depth range that it's providing was better compared to the other cameras. This camera has an API that uses triangulation to calculate 3D coordinates, and we have made two different approaches where we will talk later on, where we first use the data from the camera API. Also, this camera has a tool provided by the manufacturer Stereolabs to calibrate the camera, but it usually comes with a design calibration file by Stereolabs itself made in a lab. So we assume that like if the camera is not really old or damaged, then this calibration file should be way better than when you do it yourself actually.
And when we actually calibrated the cameras we have, it's not that different from the factory settings.
No, the changes were really small, so that wouldn't have any big influences on the output, we would say. So Max is continuing now.
Okay, so for object detection we chose to use YOLO network, which is you only look once network. The full version is presented kind of here. It has 120 layers with three YOLO detection layers. But this kind of network is too big for us. Originally was designed to detect 200 objects, if I'm not mistaken, and is capable of detecting up to 1,000. So there is a lot of space in convolutional networks for multiple features for different objects. So we didn't wanted that, but it's still the base architecture we were working on. So it has a multiple convolutional layers, then detection layer, then it upsamples then it's upsampling layer. Then we have again convolutional, and so we first we go down, we detect very big objects in the first detection, then we upsample a couple of convolution layers, we detect smaller objects in the second detection, and then we do the same again, and we detect really small objects in the third detection. So how the actual detection layer works is that why is it looking only once? Because we're dividing the entire picture to the grid, and then we have each cell responsible for detecting multiple bounding boxes. And this value is fixed usually from 2 to 4 bounding boxes per grid. So we have, in this case, 3 bounding boxes per grid. So this cell is responsible for detecting the dog. And it will give object score, obviously, and bounding box coordinates from that. So to train our data, to train our network, what we decided to do, we made two approaches. One is with transfer learning, where we take the pre-trained convolutional layers from ImageNet essentially, and then we train only the detector on the data we have. Why is that? Because we didn't have any annotated data at all, so we had to go through approximately 700 images and annotate them hand by hand, which is actually pretty sizable amount already, but still not big enough. We tried to get the data from two light conditions. This is an example. It's not seen, so it's dawn essentially, and then the other one was actually in winter and snow. So the roughest lighting conditions we were able to have from the last year's data. And the annotation works like you have a class ID, and then you have coordinates of center, bounding box, and height width essentially, and you have pairs of picture and then the file with annotations. So, and in the end, our architecture looked like that. We had actually two iterations of architectural changes. First, we tried to remove the first detection layer and corresponding, we tried removing convolutional layers as well, each one, but that didn't work out because it was not precise enough with removing of these convolutional layers. So instead, we just removed the first detection because it is supposed to detect bigger objects, and we, by nature of our project, don't really have a big cones in there. But then in the end, after experimenting, we found out that actually the more closer to original network works really good, and the only thing we did in the end was changing upsampling in this layer from 2 to 4, essentially making last detection detect even smaller objects or be more refined in smaller object detection. And of course, skip connection had to be moved to corresponding convolutional layer at the start. So there are skipped connections to retain the feature, the learned features from previous convolutional layers, to remove vanishing gradient problem and so on. What we also did in the end with the whole network is that you only look once a network is relying on entry box detection. So you have a series of entry boxes, and each entry box is responsible then for certain size of an object. And we recalculated the entry boxes for our data, for our specific data. There is a preset entry box set, which is designed again for these 200 objects detection. In our case, it was still 9 entry boxes, but they were smaller essentially. We had a wider variety of small entry boxes. So entry boxes are changed, and the upsampling is changed. And this architecture is in general not full YOLO, but this is tiny YOLO, so it has 27 layers, I believe. So it runs faster, of course. And after we detect the bounding boxes, we then do a post-processing with that.
So yeah, if we, this is the first approach that we were following, no, that is actually not true. The first approach we were following, we were taking the distance in there, and width from the API provided by the camera. And because this API says that it has an error up to 20% in 20-meter distance, we thought about having our own approach to try to make it more stable. So what we have here is the principle of a pinhole camera with the camera center in point C here. I think we kind of saw that in the last presentation already of how it will run. And with the data of the camera, actually, were able to figure out the 3D point, calculating from the 2D point in the image frame. by that we were coming up with, or not, we were not coming up with that, but Harley and Zimmerman were coming up with the calibration matrix K from all these things, putting it together, and so we got our points calculated by, yeah, this nice formulas here. I don't know, I don't have to want to go too deep into that actually right now. The approach to calculate distance by size is actually the following. Like, we were looking into the picture and we saw this bounding box we got from our detection, so we got the height of our cone, and by the height of our cone we tried to calculate like how far it is away, because we were knowing the size of a cone in real life, and we got some results there. Oh no, this is first another result.
Yeah.
Should I continue first?
Yeah.
So with the first approach, like what we get from the camera API, I don't know, it's hard to see now, like you can just see the yellow points in here now, I guess. What we did was an accuracy check to check how accurate our system works actually. And the first test was about having cones in 2, 4, and 6 meter distance, like one, like always the camera center is here, like where the car was standing actually. So we have like 2, 4, and 8 meters here, and we have like -1 and 1 and the center here. And then we were just measuring where our system was detecting the cones and where they actually should have been. And we made some error calculations from that. But first, compared to that, we have, this is our second approach where we don't take the camera API. This is the approach where we take the new calculation method by size in the picture. Like what we have to say as well is like the problem in this first try, like is like overall to say, like I think we have to make all those checks kind of again, because we changed a lot of things in between. And for example, this first test was inside the lab, and I think the detection, everything works way better outside. So one of the biggest problems was that no cones further than 8 meters were detected actually by the system on the inside. And when you look to the next one, then we have a cone distance like they were detected like further away than 30 meters, like a big improvement actually in that case. Comparing the errors now, like if we have to like just take in consideration the distance, like that we get by the camera API and that we get by distance by cone size, we can say like that we get a smaller error by cone size. And also if you think about that we are able to detect cones that are really further away, I think that's kind of improvement already to our system. However, what is a bit strange and what we need to figure out, because this were the latest tests we were just doing now, is the error to the side is way bigger with the new approach, and this is kind of strange because like originally we were calculating the width in the same way, like left and right. So we have to look into that, what is causing these problems actually, because
theoretically the error should be the same, completely the same.
yeah. So we were kind of confused by that, but yeah, I have some more here with yeah, you see the error is way bigger than here.
How should we read this?
Ah, yeah, sorry, that's a bit confusing maybe. I looked too much at those already, I guess. Sorry, so what we have here is, this is, first of all, this is like the measurements to the left, like 1 meter to the left, depending on the distance 2, 4, and 8 meters here. And then we have the error in meter and the error in percent here. And then this is the first approach by camera API, and this is the second approach, distance by cone size. So
but again, actual distances are a bit different, so
yeah,
also
we have to repeat this test, I think, and see what is the new outcome. But this was just the first test, like to have something to see how the system is working, to verify how big our error actually is. And yeah, it's far from being completely done, but it's the first kind of measurement. So I think you can continue on.
Yeah. How we measured improvements, I guess, in our tradings of the network is by mean average precision. So we divided the training data to training data and validation set with 20 to 80% ratio, so 20% for validation set, and mean average precision is essentially well, average accuracy across all classes for validation set. So with the latest network, we were able to achieve 98, 99% of map, while not overfitting actually, because yeah, some improvements were made in that regard in yeah, in skip connections and in cost functions. And with average loss of 0.8 to 1, while in previous version of network, mean average precision was actually around the same, 97, 98, but average loss was bigger, 1.2, 1.5. We also tried to train the data with transfer learning and without, because we actually realized that 700 annotated images is not that small, and with tiny yellow architecture, it's not much features to train, and in general, it's not much features to train. So we will be looking in comparing all these results, because we have a bunch of trained networks with different parameters and architectures and aspect ratios of the videos. But in terms of training, this is what we had, and we were training for 6,000 iterations, because it's by YOLO creators, it's advised to train the network for 2,000 iterations per class. So since we have 3 classes essentially, we were training for 6,000 iterations with learning ratio decrease in the last 80%, like that, for 4,080 and 5,060, I think, was 2 learning rate drops when we tried to nail down the smallest features. And yeah, of course, all the results visually, it looks really good, at least in the good sunlight, but we don't have yet any graphs comparisons and so on, because we only got now the testing data, so we will extract the images, re-annotate them, and create a good testing set that we will run against all our networks to get actually get accuracies and stuff. And yeah, the frequency, as you saw, was about 18 hertz, 18 frames per second on HD resolution. That is with 25 objects detected. When it's less objects, it's usually faster. More objects, which is not happening really. 25 objects was that picture with the entire track scene. And then it's HD resolution. So originally our goal was to run that on smaller resolution, and then it runs on I believe 35 frames per second. So it's pretty decent, and while network was trained on lower resolution, we can actually also run the inference, we can run it on lower resolution. So for instance, for drag drive, we can run HD, and for acceleration event, where we don't need that precise cone estimation, we can run faster resolution, small resolution, to get faster inference time. And with discussion, well, we need to get now the testing data for detection results, and we really think that we will benefit from merging 2 depth detection techniques, if not 3, because yeah, Olin came up with one more depth detection technique, but what we want to do is, it seems that the closer the object is, the worse the prediction of depth by size is, but in the same time, there's a big chance that depth camera is already giving a decent result in that regard. So we want to compare certainty of depth versus certainty of cone detection, and take the one that's more certain about things. And maybe if none of them are, then we can take the third one, which is based on just perspective. Then we actually need to retrain network with correct red cones, because now it's trained like it's we actually have 4 classes in our network, while we have to have 4 classes while we trained only for 3 ones. So we have big red cones and small red cones. It's the same thing. So it's confusing when you're trying to detect a red cone. The bounding box is bigger or smaller or jumping weirdly, and especially with approach of relying on bounding box size for depth detection, it's really not working. So we have to retrain that part and re-annotate the data to some extent. And I think we should have to test the different weather conditions. For now, the sun was working really fine, but like when I'm testing cam detection in the dawn, it's not that good. We cannot detect further than, well, yeah, 13 meters, I would say. Yesterday, that test was after 13 meters. I wasn't able to get any detection. It was in the late evening with no sun. So it will be interesting to see that as well. And
That's it.
we don't have the next slide.
Great. Thank you very much. So then we leave the floor to the opponent.